Alright, another draft physics video presentation. Yeah. Alright, this one's going to be one of the reply style videos to a Veritasium video, which is so bad. And it's just so depressing. So the more money he gets, the more cartoonish the videos can get, the more, nonsense and gimmicks. And it's just so bad. So, he's going to claim that he's going to prove something about relativity in this video, and he just presents the same old dead, stupid, idiotic arguments that are, easily countered with, the context of, well, there's a whole bunch of facts you left out of that scenario, and so I'll provide you some of those facts and just point out how really bad science this is. They really are just religious advocates, trying to sell a fable, a silly story about some sort of bent thing, in space that somehow causes things to move, towards each other, pull, some sort of magical mechanism. And it's still quite magical. He doesn't give us any territory, any place to see anything that could be called physics anywhere in the explanation. It's just terrible mush, and it's pitiful. This is the best they can do, selling a horribly evidenced fable. Some kind of little critter walking over there. I guess I won't disturb him. Anyway, so gets on with the show, such. So relativity nonsense. And it's all going to end, his proof is going to be the Eddington experiment again. I mean, just so bad.
This video was sponsored by Caseta by Lutron.
Oh, Caseta by Lutron, or whatever the fuck that is. I mean, it doesn't even sound like something a rational person would be promoting. What the hell is that? It sounds like some sort of disease, actually. Too loud.
According to the general theory of relativity, gravity is not a force. There are no gravitational fields. Gravity?
Okay, whatever. It's not a force. Okay, it's not a mechanism. It's not a real thing that pushes or pulls or does anything. It's some sort of magical roller coaster thingy, track, whatever. It doesn't make any sense. It's some sort of cause that basically causes something to do exactly what a light bulb does in reverse. Okay, the inverse square law, which is the most common thing in like the physical universe, is this idea of point sources and radiation and how it's all even and symmetrical. And gravity's doing exactly that, okay, except in reverse. It's clearly obeying all of the physical mechanisms of physical things that cause effects, not unphysical, magical, bent, whatever. I mean, you could explain a light bulb with an Einsteinian bent theory. It doesn't, but it wouldn't explain a light bulb. You could come up with some crap that, explaining how the photons have to come out. I don't know. I don't even know how, the bent path would end up being crooked path. I don't know. But anyway, it's the same thing. It's just a way of explaining an inverse square law that is affecting how pressure changes, you could argue. But to say it's not a force, like he knows it because he has some sort of evidence. He doesn't have any evidence. He just likes, look, I'm playing cartoon characters. I'm playing dress up. I mean, it's just pathetic.
Is kind of an illusion. And in this video, I will prove it to you.
Kind of an illusion? What illusion of what? Where's our illusion? Your whole argument is that we're not aware. So the illusion is what? Something we're not aware of? You can't have an illusion that is invisibility as an illusion. You know what I mean? So the whole argument I'm going to make here is that obviously the force of gravity, like the other forces, happens to our little bits, the nuclear bits. The electrons and protons are affected by the force. They're the things that are actually moved by the force. So obviously if the force is moving all of them, every one of them, then you're not going to notice any difference because your physical body isn't going to change. But if you're being accelerated by some other force that actually has to go through your skin first and through one part of your body first, well, then you're going to feel that pressure difference because it doesn't move all of your parts evenly. where gravity does. So, I mean, the whole thing could be debunked by basically just saying, oh, gravity's a nuclear force, okay? It happens to the smallest bits. There's only one universe, Veritasium, the small one. All this other little fake spacey exploration, all that wooey stuff, that doesn't mean anything. Electrons and protons are deciding where the moon's going to be. Electrons and protons are deciding where the Earth is and what it's doing and whether it's spinning and all that crap. It's electrons and protons. The big things don't do anything. The big things do exactly what the little things tell them to do. The big things are all just being run by little things inside of them. You don't understand that?
By blasting off into outer space. In 3, 2, 1...
So he uses like switches, toggle switches from the 50s. So they can't even build this little whatever they built, this studio, and use like a modern, cell phone or something, a touch screen. No, toggle switches from the 50s. So all of this, you need all of this to make an argument. Oh, I'm proving relativity. Yep, this is how you prove relativity, is by, telling an animated story. Pinocchio is very convincing, Disney. The Bambi, very convincing, You kind of feel like Thumper's a real thing, a real rabbit. And all the characters are kind of real, So yes, we can be fooled. So who's doing the illusion? Who's playing the games with people's perception? Somebody has to make these kind of arguments. Special effect arguments.
Albert Einstein said the happiest thought of his life was imagining a man...
Yes, he said lots of things. So what? This idea that everything is equivalent to everything is just stupid, and that's essentially what he's saying. It's not even a rational equivalency principle.
And falling off the roof of a house. What made Einstein so happy about this wasn't Schadenfreude. It was the realization that this...
Schadenfreude, means getting what you deserve. So, Einstein wasn't imagining his landlord falling off the roof, because that would have been Schadenfreude.
Man, while he was falling, wouldn't feel his own weight. He would...
Yeah, he's never going to feel the force that's acting on him. That's exactly the point. So the force of gravity is acting on every single one of his atoms. So all of his atoms are being accelerated exactly the same speed. Exactly. Okay? So his stomach doesn't know, his pancreas doesn't know. They're all moving at exactly the same acceleration. There's a boot on all of them, pushing all of them at the same time. So he can't feel anything because they're all being pushed exactly the same. So how can I feel the change when when there's nothing changing? When I'm not leaving anything behind? When everything's being pushed exactly the same amount? So I don't feel it. Now if somebody puts an actual boot on and stomps me in the head, I feel that force, because it doesn't affect my stomach and my brain at the same time. It doesn't affect every part equally. It affects them very unequally. So I feel it. I sense it as a disturbance in my, peace and and the tranquility of the integrity of my physical form, because it's going to be violated by causing it damage by changing part of it without changing all of it. It's going to be unevenly applied, this force. So the obvious argument would be the force of gravity, like photons and like all these other things that we know about, these little tiny things like magnetic stuff, is going to be something we're not going to feel. I can put a magnet on one side of my hand and a magnet on the other side of my hand. I'm not going to feel the magnetic force. Now I'll feel the pressure of the two magnets, but I won't feel the magnetism. Oh, yeah.
Be weightless. And anything he dropped on his way down, well, it would remain stationary.
Yes, but it's in exactly the same rain, okay? It's all being hit by the same little tiny rain. A little bit of rain is falling on everything, and it's hitting it and pushing it. And it's that simple, and that's the force. And it goes, like I said, it's happening on the small universe scale. It goes right through atoms, goes right through everything, and hits electrons and protons. Ugh.
Relative to him, or moving in uniform motion. The whole situation would be just like if you were in deep space.
So we know there's gravity where the Earth is, and that if I move far enough away from the Earth, the gravity diminishes. That is, this idea that there's a difference in the force diminishes. So if there was an idea that their force is even, okay, if I'm in space, plain space, there's just as much gravity hitting me from one side as the other side, just as much force. And then if I get near Earth, I'm being shielded from some of that force. Some of that force is being absorbed by the electrons and protons of the Earth, and it doesn't get to me. And that's what's moving me towards. So I'm always in force, and all we're really saying is you're always being pushed, and sometimes one of the pushers gets weak, and then the push gets realized into a movement. So it's a tug of war, the opposite of, the inverse of. It's just two things pushing. And if one of them stops pushing as much, then the thing that's pushing harder wins. That simple explanation fits. Okay, it doesn't need any help. And again, when they teach special relativity, they teach it as mock gravity. They teach it as a force from the outside in. They teach it as a vacuum cleaner. I mean, damn. Where was I? Yes, hit the button.
Not near any large masses. With your spaceship at rest or coasting along at constant velocity.
So, yes, obviously if it's coasting, that means that you've already done the accelerating part, so everything in the room wasn't flying freely. You had your rocket ship push it all to the same speed. So it didn't have any of this floating around thing, wasn't happening while you were accelerating. That only happens when you stop accelerating. So when you stop accelerating, then you can pick the stuff up off the floor and let it go, and it stays wherever you let it go. So again, just more, these are important little facts, little pieces that give the puzzle away. The Einstein argument is that it's equivalent and that you can't tell. And that goes back to, Galileo making these kind of arguments. And the truth is that you can tell whether you have velocity or whether you're accelerating by just opening a window. So this whole thing is just such a pile of crap. There's no experiment you can do. Yes, there are experiments you can do. You can open the window.
Here, you would feel no weight. Objects would remain stationary relative to you. Or if you give them a push.
Yes, you never feel gravity because it moves all of your parts equally. And that's you can't feel something until it does something uneven to you. It has to be a difference between what's happening to the surface and what's happening deeper inside. Gravity hits it all, okay? So it moves it all. So you can't push your flesh with gravity because, it's going to move the interior flesh just as much as it moved the outside flesh. So the whole point of these forces is that they act on the nuclear bits, and they move all of the atoms and all of the bits at exactly the amount of velocity proportional to how many atomic bits there are. The only thing that can be moved is electrons and protons, and they're moved a standard amount by the presence or absence of this rain that's always this fog that's always in the universe pushing on everything. That explanation works just fine.
They would move in a straight line at constant velocity. And you would be the very definition of an inertial observer. You're not accelerating, not in a gravitational field. All the laws of physics apply in your reference.
Right. Now, of course, you are in a field. You just don't know it because you can't feel it. So you could be in a magnetic field, you could be in a gravitational field, all of those things could be true, and you're just saying, well, I'm not because I said I'm not. Well, did you prove you're not? I mean, there's no place you could really go in the universe and play this game, because wherever you go, there's going to be unevennesses. There's going to be a little bit more mass on one side of you than there will be on another side of you. There'll always be some unevenness. There's no place you can go where you're going to have exactly the same amount of mass that's, within 15 miles of you, and exactly the same amount 40 miles away, and exactly the same amount 100 miles away. That ain't going to happen anywhere in the universe.
Frame, meaning there is no experiment you could do to distinguish.
Right. It's going to show the light clock experiment later. It would clearly show you exactly how fast you're going. Clearly. So this is the irony of it. There's no experiment you could do except for the light clock one, which will tell you anything you want to know. Now, obviously, it's only going to tell you if you're going really fast. So it only works when you get up to really good fast speeds. But the truth is, it will tell you. Photons are reliable by Einstein's own words and Einstein's own theory and Einstein's own thought experiment. So unlike what the people say, Einstein didn't predict that the light in the spaceship jumps forward. Okay, he didn't predict that. So you can keep saying it, but that ain't the truth.
Your inertial reference frame from any other. Now here comes the big leap. Einstein looks at these...
You're not calling it a big leap. You're sitting there arrogantly saying you have proven it. You've given us this preponderance of the evidence, this huge volume of evidence proving any of this crap. No, there's no proof that there's no force of gravity, and there's certainly no proof for any made-up nonsense about some bent geodesic to explain the inverse square law, because, frankly, it's just bullshit. You don't need it. And you could do the same thing. Again, you could use bent space to describe why, light emanates from a light bulb, but it wouldn't explain what a photon is.
Two scenarios and says they are equivalent, not just similar. Physically, they are exactly the same thing.
Right, when they're not. They're clearly not the same thing, because in one example, like when you're standing on the Earth, there's two forces involved. There's a force pushing you down and the force pushing you back up. Right? So that's two forces. So there's no point in comparing a point where you're being, number one, pushed by one force you can't feel, gravity. So you'll never feel gravity pushing, because gravity always pushes even. And the only reason why you feel the ground pushing you up is because it's not gravity and it's not pushing you evenly. It's either pushing you on the feet or it's pushing you on your ass. But it's pushing you physically from the outside of your physical body. It doesn't move your stomach and your pancreas and your liver all at the same time. It doesn't do any of those things. So the force pushing you back is completely different than the force pushing you down in terms of how it interacts with your body. Completely different. And that's why you feel different. But that's the only reason why you feel different.
Which means man falling from roof is not in a gravitational field. There are no gravitational fields.
So again, it's just like baby talk. There's no gravitational field. It's just magical magic. No, it's not an explanation. Things just happen to go in the direction of a matter. It just happens to be, vacuumed there or magically compelled, there's no mechanism. It's just absolute nonsense to say it has something to do with curved lines, because curved lines aren't going to initiate your velocity, and they're certainly not initiate your acceleration. And if I start you far enough away from the Earth, just standing still without any velocity, by the time you get to the Earth, if I put you like out at Mars and just like you slowly be attracted to the Earth, by the time you get to the Earth, you're going to be a speeding bullet. And you're going to hit the Earth going, insanely fast. You're going to burn up in the atmosphere. You're not going to do any of this, I'm just floating, yay, I'm just geodesicing. None of that shit. You're going to burn up.
And he is not accelerating. He is an inertial observer, just like Rocket Man. Whoa. Okay, I can see how both of these observers feel weightless. But
yeah, why don't you say, I can see how, look, okay, both the force, you'll never feel it. So it doesn't matter what it does to you. You'll never feel it because it's moving all your parts at the same speed. Right now there is some notion that when you get near like a black hole that you would get spaghettified. That is, it'd be a very unevenness in your gravity from your head to your toes. And so you would feel the spaghettification. So the argument could be that, no, it's not even an absolute statement that you won't feel gravity. Because if there's enough of it, it will in fact rip you to pieces and you'll feel getting ripped to pieces.
Man falling from roof is clearly in a gravitational field. I mean, he's right next to the Earth.
So all we have to do is make the gravity a lot stronger, and this whole analogy falls apart, right? Because if we make the gravity more than 10 meters per second squared, and we talk about black hole kind of style gravity, then all of a sudden his hand starts getting pulled a lot less, okay, get pushed, but regardless, less than his right and his left hand are different, and the feet are different. Now every piece of his body will start stretching and pulling apart, and all his little guts will pop out, and everything else, he'll turn into a bloody mess. And now you won't be saying how he's just feeling nothing. You'll notice that he does feel something. And when he does that experiment in a spaceship, okay, when he gets spaghettified, let's watch me get spaghettified, you'll be able to do an experiment that'll tell you I'm in a gravitational field, because you're going to get spaghettified and your guts are going to fly out. So this idea that you can't do any experiment to tell, well, yes you can. So if you have enough gravity, you can do the experiment of being spaghettified.
And he's obviously accelerating. His speed is increasing by 9.8 meters per second every second, a fact that will become painfully apparent when he crashes into the ground. I know that these two situations look very different, but Einstein's equivalence principle tells us the one...
It's not a principle, it's not anything, it's just a little slogan of Einstein's. It doesn't have any backing by anything evidence-wise. It's just a statement, and it's a statement you should never even touched, because they're not equivalent forces. So if you compare gravity to gravity, a force that affects all the little bits the same, then it's a fair comparison. But again, as I just gave you an example, all I have to do is change the amount of gravity, and I can show you quite a huge difference between the guy in no gravity, zero gravity, whatever you want to call that, and the guy in intense gravity, because one guy is going to become a bloody mess and the other guy won't be. So how can they possibly be equivalent then? Oh yeah, that's right, no equivalence anymore.
Thing to focus on, the experience of the observer.
Right, the experience of the observer is going to be, I'm getting spaghettified. My feet are going faster than my head. I'm being stretched, pulled, and then ripped to pieces.
If they feel weightless, then they are in an inertial frame of reference. Every bit as good as Rocket Man's.
And again, what is feeling weightless? Feeling weightless just means that all your parts are getting moved the same speed. So we feel weightless from our feet or from our ass up, right? Everything feels weightless because there's no effect of gravity. We don't feel it. And the force that's pushing us up is distant. So you really don't feel being pushed. Your hands don't feel it. Different parts of your body don't feel the gravity nearly as much because they're distant from the actual force.
Without drifting through deep space. Imagine if Rocket Man, coasting along at constant velocity and not paying attention, comes upon a planet a long way off in the distance.
All right, so this analogy you fix by just saying, no, let's say Rocket Man is doing what you just said. He's standing still. He's just stopped in space. Okay, and we push him, we just slide him over into the gravitational field of a planet. We just push him into it. And then we just let it go and say, what is it going to do? And it's going to go in a straight line right for that planet. It's not going to travel any curved lines for your convenience. It's not going to play any of the games you want to play. It's going to move in a straight path right towards the planet. Straight, dead straight line. No bent geodesics, no nonsense, no two forces. There's only going to be one force applied. There's not going to be two forces, your acceleration and some bending force. No, there's going to be one force, a dead straight line right into the planet.
An external observer might notice that the path of the rocket bends ever so slightly.
Right, see, so he's using the path of the rocket. There's no path. Let's say we just get rid of all that path stuff. No velocity. We just stop him zero momentum in the universe, and we just let him go and see where he goes. He's going to go straight line right for the middle of that planet.
Towards the planet. But inside, Rocket Man would remain oblivious.
So there's two forces acting on that. So mathematically, every curved line is made out of straight lines. And so all you do is add up the straight line of the amount of force that's pushing at an angle towards the planet. They're straight lines. So it's like measuring how much light is hitting you. So if the planet was a light bulb, you're just measuring how much light is hitting me. And as you turn, as you know, you move towards the planet, more and more light hits you. So you're more and more pulled faster and faster in that direction. So you're just pulled based on, well, pushed, but, you know, the absence of push. There's less push the more you move towards the planet. So if you thought of the planet as creating a shadow, and the shadow was attractive, you could understand that the shadow is what's just going to compel you. So you're traveling a curved line, but the curved line is clearly made out of straight lines.
He feels no force, experiences no acceleration. As the rocket gets closer to the planet,
you'll never experience gravity. So it doesn't matter until I put you in super strong gravity. So until you start talking about really strong gravity, you won't feel it, because yeah, it moves every piece of your body evenly. So how can you possibly feel it? Just like me and the flashlight, and you know, if we're in a rocket ship and I'm holding it, there it's going to acquire the same velocity I acquire, and so I'm not going to be able to feel any difference. I mean, I actually will feel the flashlight because I will have to accelerate it. The acceleration will have to actually go through my hand. So again, it's not a good example. Physically accelerating your flesh through the outside in without using a force means you'll always feel it. And if I use gravity or magnetism or some other minute force moving the speed of light, if I use one of those, you'll never feel it. Except when I apply a whole bunch of it. A huge imbalance of it. When there's a huge imbalance of it, you're going to feel it.
It goes faster and faster. But Rocket Man still feels weightless. For him, nothing has changed. So where on this journey would you say the frame of reference changes from inertial to non-inertial? An onboard acceleration.
The whole concept of inertial and non-inertial doesn't mean anything. So, you know, you either have momentum or you don't have momentum. And clearly we have momentum because we're on a planet that has momentum. That planet's in a solar system that has momentum. That solar system's in a galaxy has momentum. So we have lots of little momentums. So we'll never be in any inertial frame.
Barometer would never even register a blip. He has continued on his inertial path through space-time. So the logical conclusion is his frame of reference is inertial up until the instant he crashes into the planet.
Or crashes into dust, or crashes into a helium atom, or anything in his way at this very high speed. So if he's going at very high speed, he could bang into lots of things. And he's still in his whatever his frame is. It's just that now his rocket ship might have a few holes in it. So, I mean, it's just silly. There's no inertial frame. There's no whatever. There's either you get affected by a force, okay, force in its native form, okay, which is little bits moving the speed of light. That's what all the force is made out of, is little bits moving the speed of light. If that's affecting you, it's affecting your electrons and protons, and you're not going to be able to tell because it's going to affect all of them evenly. Oh, what other way to make an example? No, that's all you can say. And it's only when you're affecting them unevenly that you can feel it. So only when a force is applied to you unevenly do you feel it.
Okay, so how do you explain the curved path of his rocket without gravitational forces or gravitational fields? The answer is curved space-time. First, focus on Rocket Man's observation that...
So just understand, all you need to understand is there's a bunch of straight lines hitting you from behind wherever you're heading. So whatever the object is you're looking at, just think of a bunch of straight lines going right to the center of that object, and they're always pushing you. So if I'm going against those lines, they're still pushing me. And so there's going to be two vectors. There's going to be the vector of your momentum, and then there's going to be the vector applied to your momentum. And that's it. So there's two straight lines, and they tell you where your next location will be. The two straight lines calculate the solution. And that's how it's always calculated. It's always calculated that way. It's not calculated as a curved line. It's calculated as two straight lines intersecting.
The whole time, he felt like he was moving with constant velocity in a straight line. He was moving in a straight line through space-time. But space-time around massive objects...
So more nonsense. Obviously, he was moving in two different directions. He has a velocity of his ship, and then he has the velocity of the gravity. So there's two different forces, two different vectors. Again, if I started him at nothing and let him go in a straight line, then we wouldn't be talking about any of these geodesics.
Objects like planets is curved. So that's why his path appeared curved to a distant observer. Now this isn't...
So who falls for that, right? I mean, it's just such a bogus. Like I said, all I had to do is change the starting position. Start him off with no velocity, then there won't be any curved line, and you can't pretend, oh, look, it's a curved geodesic. There won't be any curved geodesic. Just be a straight line right to the center of the Earth, right where he'll crash right into the, middle of the Earth.
As unusual as it seems. Airplanes, for example, always try to fly the shortest route between cities. Essentially, they just go in a straight line. But since the Earth's surface is curved, the shortest path doesn't look like a straight line. These shortest paths over curved surfaces are called geodesics, and we use that same word, geodesics, for the straight line paths followed by inertial observers through curved spacetime.
But again, there's only a curved line if you're applying two velocities. So if you just use the thing that's causing the effect, it'll look just like a light bulb. Nobody thinks about the light bulb and says there's a bunch of curved geodesics. Well, there would be if you're being affected by light. Let's say the light was pushing you and you applied a velocity. Well, then obviously you would curve away from the light. If the light was applying a pressure, you would curve out of the pressure of the light. But the light, it's a bunch of little straight line rays that are deciding how much you're going to get pushed. So I mean, there's this bent geodesic stuff is just a dodge. It's just, there's no physics to it. There's no necessity for it. It's the emergent thing that never really exists. Again, the curved path doesn't really exist. You really are sitting on the Earth being pushed up and being pushed down. You are actually, part of your body right now is going up. Part of your body's going down. The two forces are always still working. They're always moving you. Bits of you are being moved by them all the time.
Here's another analogy. Imagine you and a friend are standing 1,000 kilometers apart on the equator. Now you both set off...
you do understand that you're actively pushing into the Earth all the time. You don't just push into it once. I sit in my chair, there, I pushed on the Earth, and that's the last time I'll ever hear from the Earth again. No, you're constantly pushing. You push into it, it pushes back. That's what's happening. So you have to understand that you have to be moving both ways.
North. Over time, you will come closer together, ultimately bumping into...
Right. Yeah, so what? Again, I could just draw a bunch of rays coming out of a light bulb and they all converge. So what? This doesn't mean a thing.
Each other at the North Pole. It's as though there was a force pushing you together, but you didn't feel a force.
Right. So this has nothing to do with that analogy. It doesn't explain anything about why you're being attracted to the Earth. It doesn't explain, like I said, if I just put something out in space, by the moon somewhere, except not next to it so it doesn't get gravitationally moved towards it, I just stuck it out there and it's going to move right into the Earth. This stupid analogy doesn't explain to you why it moves. This will not explain it. Okay, the fact that the rays converge, everything turns into a point source of convergence, that is not news.
And your friend didn't feel a force. Gravity is just like that force. It doesn't actually exist.
So again, there was no force that pushed those two people together. There's just an absence of space. They ran out of space. There's no force pushing them together. There's no mechanism pushing them together. If they stop walking, they don't move into each other. So again, his analogy falls apart because it doesn't mean anything. There's absolutely no motion here. There's nothing compelling them to move except for the fact that they're walking. So stop them from walking and then show me why they move into each other. There's no necessity for them to move into each other. They wouldn't move into each other. If they're not walking and they just stay right where they are, they'll just stay right where they are. I mean, this is a terrible analogy.
Reason for you coming together was that you were both on straight paths, geodesics, on a curved surface. Astronauts on the space station are weightless. That means they too...
So again, it's stupid to call them weightless because what they are is they're compensating for the amount they're falling into the earth. So they're still falling into the earth, and they've compensated with a velocity that keeps them from crashing into the earth. So they're still in strong gravity. They're still being affected by gravity. It's just that they're applying another force that makes that force not make them fall into the earth. So they're free falling in that sense. They're falling, but they're constantly being pushed by their momentum, and their momentum they've already experienced as acceleration, so they're not going to feel it anymore. So they have momentum, they have velocity. The velocity is like once you've taken off in the rocket and then you stop, turn the engines off, you're not going to feel acceleration anymore. So they're not going to feel the acceleration of they're not going to feel their velocity once they stop accelerating. So there's two forces affecting them that they can't feel.
Are inertial observers traveling on a geodesic. But the Earth curves space-time around it, which is why their straight-line path appears as a helix. It only looks like a circular orbit if you forget the time dimension.
Oh, it has nothing to do with the time dimension. The moon's doing the same thing. I mean, the Earth is spiraling with the sun, so the Earth is doing the same thing as this, because they're both moving in another direction. So this is just adding up momentums. But they're all momentums you can't feel because they're not accelerations. Once you have velocity, you don't feel, because nothing's pushing you anymore. Nothing's pushing you up in the ass or pushing you in any way to accelerate you. So this is just an argument about the difference between acceleration and velocity. Non-accelerating velocity.
Don't forget, we are all moving through space and time. Space-time. This is the standard...
It's just really so obnoxious. I mean, even religious people don't do this kind of thing where they do this we thing. We. Like, we all have to believe this. Like, oh, yeah. You know, I mean, it would be better if they say us Christians. You know, that would make me feel a little better. If they weren't so obnoxious as to think I want to be part of their religion. Ugh. I'm not one of yous. I'm not one of your we.
Bent sheet analogy for curved space-time. But I think this demo is misleading. It allows you to fool yourself into thinking...
Well, first off, it's never proportional to the real circumstance, and yes, it's using gravity to illustrate gravity, which doesn't make much sense. You can't explain a force using the force you're explaining.
You understand general relativity, when the intuition you're actually drawing on is just that objects like to fall towards the middle of a well due to the gravitational force. But in general relativity...
Well, that would be really silly just to think they want to fall, okay, because obviously you gave them motion or velocity, and the amount they're falling isn't nearly as significant as the velocity you gave them that keeps them from falling.
There is no gravitational force. What you should be thinking about is objects traveling on a straight line path through space-time. It just so happens that space-time is curved around massive objects. So that straight line path...
So again, he's using a thing with velocity, where if you just take away the velocity, you don't have any curves to talk about. And it's just a dead straight line right into the center of the Earth. So he's drawing the straight lines right there for you to see. So why do I need this curve crap? Okay, the falling part's going to happen even if I don't have an initial velocity. I'm still going to fall. So it's not about bending a line. It's about the fact that for some reason I'm going to get pulled into the earth, and you're not applying any reasoning. You're just saying because the lines converge, I will have momentum, and I will gain more and more acceleration. The closer I get and the closer those lines get to each other, somehow I'll gain more and more and more speed, but you're not explaining anything about what's causing that. Why does that make any sense to anybody? No force did it. It just happens. The earth just happens to have this charming personality that just compels everything to fall into it. No, it's stupid.
Doesn't look like a straight line. Matter tells space-time how to curve, and space-time tells matter.
Yeah, it's stupid. Space-time isn't a thing, so a nothing tells a something what to do. I mean, that's what he's saying. Nothing tells something what to do, and something tells nothing where to be. I mean, it's just so stupid. Oh God, you're such a a queer little Borg you people belong to. I mean, just this is just such frickin' it's Teletubby stupid.
Matter how to move. Now let's go back to deep space.
I'm cool, that's me. So he just makes these statements as if, yes, we've proven something. Haven't proven any of this. This is just a fable.
What happens if you turn on the rocket thrusters and accelerate at 9.8 meters per second squared? Well,
you won't get hit with a force that's anything like gravity. So that's the truth, right? So unlike gravity, which is affecting every single electron and proton and moving all of your parts evenly, nothing like that's going to happen at all. Your feet are going to get hit, okay, first. Or if you're sitting in a chair, your butt. And you're going to get pushed physically and unevenly. Yeah, just kind of how the earth is pushing you back. So yes, you're never going to feel gravity, so it's nothing like gravity, and you're just saying that I'm going to apply the equal force, which is the earth, which is under pressure, and the earth pushes back. You push in, it pushes back. You push in, it pushes back. That's happening constantly, constantly, constantly. You're sitting on the earth doing this all day frickin' long. Endeavor to persevere, Gary.
Someone outside would see all objects remain stationary, while the floor of the rocket accelerates into them.
And unevenly pushes them.
Inside the rocket, everything would appear to accelerate down to the ground, and you would feel a force pushing up on your feet. The same force that's pushing up on you as you watch this video.
It would just be the same amount of force, just because obviously it's the amount you push into the earth pushes back that equal amount. It requires there to be equilibrium. So whatever you push in with, it pushes back with. It's a perfect spring. So whatever amount of energy you put into the spring, it gives you back exactly that much energy out. And so it just depends on how fast you're going.
This situation feels exactly the same as being at rest on the surface of Earth.
So it feels the same. So again, this is all just about how you feel, and there's talk about how you feel in the context of not recognizing that forces affect you. Forces cause motion in very different ways. If I apply a force, I've already used these analogies, but obviously if I put all the force, all the momentum in a bullet, it go right through your head. But if I put the momentum in a big giant sheet of paper, just bounce off. It'll be nice. It'll be kind of a fun thing to do. Same momentum, same energy, obviously in a different form. I change the form of the energy you're interacting with, and I make it so it only interacts with a few, all of your high voltage versus low voltage. Same wattage. One's going to kill you, one won't.
Because we are at rest on the surface of Earth. Now I want to ask you, are you watching this video in an inertial frame of reference? Well, I mean,
you can never be in one technically, because you can never be outside of the influence of all the gravitational objects in the universe, and they're all going to be, there's no two locations that can, there's no location that can possibly have just as much crap on this side of my desk as on that side of my desk. It's just not possible.
do you feel weightless? No. So you are not an inertial observer. Your situation is exactly the same as someone accelerating on a rocket ship in deep space.
So it's not even close to being the same, because you're obviously gaining no velocity. You have zero velocity for your efforts because you're just compensating for another force that's pushing you in the opposite direction. So the gravity is pushing you into a spring. The spring is pushing you back. That's hardly the same thing as you accelerating in space at 9 meters per second, which would end up collecting a huge velocity. So after you do that for a year or whatever, you will be going the speed of light. I don't know how, it might be even less than that. But if it's just 1g, okay, and I just keep applying 1g, my velocity will get higher and higher and higher and higher and higher and higher.
And let me be clear, I don't mean that being at rest in a gravitational field is like accelerating in a rocket. I mean, it is the exact same thing.
And I mean, that's just baby talk, and it's so fucking silly to think that the two things are exactly the same when they're not exactly the same, because one's got two forces in the equation and one's only got one force in the equation. And the force isn't gravity, so it's pushing you from the feet up, which is different. So if I increase the rate at which you're accelerating, I will break your knees and then break your hips, and I will rip you to pieces. So if I just accelerate you fast enough, the two things won't be the same at all. Gravity can accelerate you really fast without spaghettifying you, right? And you won't feel it. So we could be in gravity that was 100 meters per second, or 1,000 meters per second, and we would gain velocity, and we would be moving really fast, really quickly. After 30 seconds, we'd go in like whatever 500,000 miles an hour, right? Okay, but if I did that in a rocket, I break your knees, I break all your joints, you break into pieces, because your pieces can't tolerate that kind of acceleration. The fact is, the parts moving at a different speed will rip you to pieces, because the pieces will be moving at uneven speeds, and they'll just tear your flesh apart. So again, all you do is change the velocity that he's pretending to do this little baby thought experiment at. I just change the velocity and the rate of acceleration, and he can't do this same thing anymore. Same thing doesn't work anymore.
You are accelerating, and there is no gravitational field. Gravitational fields do not exist. Now, I know that sounds crazy, but come with me for...
No, it's just silly. It sounds silly. Gravity doesn't exist. I mean, it's just silly to say, what's the mechanism then? And just, again, talking about bent geodesics does not explain why you move towards something. Moving towards is a real event, and you can't just sit there and say, bent geodesic. Because you don't get there in a crooked line.
For a minute. This is you. In standard Newtonian physics, we draw your weight force, the force of gravity pushing you down, and...
Well, that would be stupid to draw it there, because that's not where it's pushing you down. So where you should draw it, it's everywhere. Oh, yes, it's pushing all your parts evenly. Your foot is going to get pushed just as much as your head and just as much as your hand. All your parts are going to be pushed exactly the same amount, and therefore you're never going to feel the thing.
The normal force from the floor pushing you up.
Right, the force pushing you up you will feel, because god damn it, yes, it's pushing on just one part of your body at a time, and other parts don't even know it's getting pushed, and they really don't like the whole idea.
Say these forces are equal and opposite, so there's no net force on you, so you are not accelerating.
Alright, so that's just silly. We obviously are accelerating. We're obviously, to go up, the Earth will not push us back unless we push into it first. We have to push into its pressure. If we're, it's any fraction of a millimeter right above the Earth, there's no pressure. No, it's not until we push into it that it pushes back. So again, you have to incur, you have to push the electrons in on the Earth. You have to push the electrons and create more pressure between the electrons in the Earth before it pushes back. So you do have to constantly accelerate into it, and it constantly accelerates you back out. That's the truth.
But in general relativity,
It's just your acceleration is back and forth, so you're not moving anywhere. You don't gain any velocity because you accelerate this way, and then you accelerate that way, and then you accelerate this way, and then you accelerate that way. That's what the individual pieces of your body are doing. Each one of the atoms, the electrons, and the protons are accelerating down and accelerating back up, and accelerating down, accelerating back up. That's what they're doing all the time. They're constantly accelerating.
gravity is not a force. You have no weight, so the only force on you are these normal forces pushing you up.
And where would they come from? Oh, that's right. They can't come from anywhere, because if I don't push into the Earth won't push me back out. It won't reject me, okay? The force pushing you out is a force of rejection. You can't get rejected until you go into the house and, get kicked out of the house kind of thing.
So you are accelerating upwards, but I'm not moving up. Relative to what? Relative to...
So, quite obviously there are two forces and you're not moving anywhere. You're jiggling. You're going one way, this way, and then the opposite way. That way, the opposite way. There are opposite directions. It doesn't mean you're not moving. It just means you're not going anywhere. You're just going from point A to point B, and then back to point A, and then back to point B.
The flip chart and the floor and basically everything in this room, but all of those things are in your frame of reference, which you know is not inertial. Relative to everything in my rocket ship, I'm not accelerating.
Right, and so all you have to do is open the window and you'll see you're accelerating because everything's flying right past you. So you're moving relative to what you thought was not a moving frame. But there's clearly a difference. There are real motion in the universe, and if I move you enough, your atoms aren't going to like it and they're going to start to fall apart.
What you need, if you really want to measure your acceleration, is someone in an inertial frame of reference. Like the guy who fell off the roof. And he...
So again, he's not in an inertial frame of reference in the same, he's still moving through the solar system. He's still being pushed by this, the motion of the Earth, the rotation of the Earth. So he still has that motion. He has the motion of the Earth around the sun. He has the motion of the solar. So he isn't inertial anything. He's still in a complex field of momentum.
Would see you accelerating up at 9.8 meters per second squared.
But obviously, he's not seeing you accelerate up. He's just seeing the difference in your motion. He has a momentum in a certain direction. You have momentum in a certain other direction. Which one of you is moving? Yeah, you can't really tell. But the fact is you have different momentums, and that's all you can say. There's a difference when one force is acting on you that's not acting on the other guy. Would be the simple argument. The simple argument, the missing force is we are not pushing into the Earth, and so the Earth isn't pushing back. So that's the missing force. You're both being affected by gravity, but one of you is getting pushed back by the Earth when you push into it, and the other guy isn't pushing into the Earth. But if I give him a long stick, well, then he can push into the Earth, and then he can stop falling down.
I think what this shows is that what an acceleration really is it's a deviation from a geodesic.
Oh, bullshit. What an acceleration is a change in momentum, period. It's a change in the direction that the bits must travel. Yeah, the average... So see, you have to, when you have a complete object, the object can be doing all kinds of different things at the same time. So it's like a school of fish that's in one place. The school of fish, the person can be in one place, but there's cells that are, blood cells going this way, and blood cells going that way, and blood cells going all different ways. So there's stuff moving in all kinds of directions. It's just that they're net. If you add them all together, which way am I going? I'm not going anywhere.
You can't follow a straight line path through space-time because the floor prevents you from doing that. It applies a force upwards on you, so you're accelerating up. But if I'm accelerating up, and so is everyone else around...
Right, but you're not accelerating up in any kind of, like, in any real sense, right? Because that would mean you get accelerated up once and you're done. You're not accelerated up once and that's the end of the gravity problem. Your butt sits on the chair, you feel it go ouch, and then it stops and everything's fine. No, it keeps going ouch. It keeps going, I feel that, 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 I feel that. It keeps pushing. So his whole point is defeated by just making the simple point that obviously if I gain no momentum in the direction of the force, there has to be some other force that pushed me in the opposite direction.
The world, and presumably the whole surface of the Earth, then shouldn't the Earth be expanding? No. It is possible for you to be accelerating even though your spatial coordinates are not changing.
Right. The only way that can be true is that you're going from point A to point B to point A to point B to point A to point B. That you're just going forward and backward, forward and backward, forward and backward. You're just going left, right, left, right, left, right, left, right, up, down, up, down, up, down, up, down. Yes, you're accelerating constantly, but you're not going anywhere.
I will show you one equation from general relativity.
Right. Bullshit.
This says that the second derivative of your position with respect to time is equal to your acceleration. That's just f on m. And if you were in flat space-time, well, this is exactly what you're saying. If you're accelerating, your spatial coordinates have to change.
I mean, there's no even point in saying when they say force, obviously it's completely related to your mass. Your mass is the thing that has to be moved. Matter moves at a constant rate, so it's always made out of the same stuff, electrons and protons, and it always takes the same amount of push to make an electron go from 1 inch, let's say. If an electron's going to move 1 inch, always the same amount of force has to be applied to make it go 1 inch. That never changes. And if you're pushing with another force in the opposite direction, well, then it can take twice as much force. But how much an electron moves per unit of force is always a standard.
But you're not in flat space-time. And this term is related to the curvature of space-time, and this is your velocity through time squared.
Yeah, what's the point of this, right? Incomprehensible symbol, TTRUT squared. I mean, it doesn't mean a damn thing, right? So he couldn't even put those into numbers. He couldn't make that into a real thing.
You don't have to worry about the details here. The point is, your position can be not changing. This can be 0, which means your acceleration must be exactly equal to this curvature term times your velocity.
Right, but that's exactly not the truth. So I'm just saying we already know that's not what's happening. We know I'm not being pushed by the Earth and I'm not gaining any velocity. So we know there has to be another force pushing me the other way because I'm not gaining any velocity. And I know I'm constantly being pushed by the ground. The ground's constantly pushing me. It didn't stop pushing me. It keeps doing it. How come I'm not gaining any velocity?
Through time squared. So in curved space-time, you need to accelerate just to stand still. A lot of this may seem more complicated.
Yeah, right. So it's all the same place, right? So I'm 1,000,000 miles from the Earth, and that's actually the same place as being in the center of the Earth. No, it's not the same place. I obviously didn't stand still. I obviously moved through space. So this is just such crap.
Than Newtonian physics. But one classical mystery looks a whole lot simpler in general relativity, which is why all objects fall at the same time.
Because gravity's a nuclear force. Every electron weighs exactly the same amount. So yes, every one of them requires exactly the same amount of force to move. So if I'm going to move a feather or I'm going to move a lead ball, there's a lot more atoms in the lead ball, so they're going to collect a lot more force because there are a lot more electrons to collect the force. So if you just think of the electron as a piece of sail, one square foot of sail on a boat, all you're saying is, how much wind did I collect? Well, it's exactly how much sail you have. Okay, it tells you how much wind you collected. And the catch is to move the sail, it's a certain amount of mass. And so it always ends up moving the same speed. Everything moves, one square of sail moves exactly the same speed as 4 squares or 10 squares or 500 squares, because the only thing really moving are the squares of the sail. You can't go any faster than a square of sail.
Rate. Now, I have made a number of videos on this topic, and I would always give the standard Newtonian explanation.
Right, and so instead of giving the rational explanation, which is gravity's a nuclear force, it's affecting the atomic number. It's affecting the actual mass, the atomic mass of the object, and so that's the collector, and every piece of it reacts exactly the same based on that mass. So every mass unit behaves exactly the same way. So it just doesn't matter whether you have 500 of them or one of them, they'll fall at the same rate because only a certain amount of wind can hit that size sail.
The only force on a free-falling body is its weight, g(mm) on r squared, which equals its mass times acceleration. You can cancel the object's mass.
The idea that you could cancel some of this out is a good idea, just because everything makes its own gravity. I'm making gravity by having atoms that are moving and electrons and protons that are moving. And as the electrons and protons are moving, they're consuming force. They're consuming a little bit of energy to do that from the universe. And so more energy goes into me than comes back out of me. And everything else is doing exactly the same thing. Everything else is absorbing a little tiny bit of energy by moving electrons and protons. And by doing that, they're creating a void where the universe would be louder if they weren't using some of it up.
Mass on both sides of the equation, hence all objects will have this same acceleration. The mystery is why we could cancel these two m's. The one on the left was
They're on the other side of the equal sign, so they're not terribly relevant. But of course you're going to cancel one of the m's because every object is an independent gravity producer. So Newton's asking you, what's the total force between two objects? He's telling you, this one's sucking this much, this one's sucking this much. What's the total amount of suck? Well, just take one of the m's out and you'll figure out which one's sucking which amount. So that's all the equation is basically saying. It should have always just been F equals gm over r squared. That's telling you what amount of force you are going to create. Well, how big a shadow how big an energy deficit am I creating in the universe by sitting here in this chair? And that's what I'm doing. Every minute I'm sitting here, my little bits are moving. They're getting pushed by real force, and they're consuming energy out of the universe. And so there's more goes into me than ever comes out of me. And so I'm wreaking this deficit. And everything's wreaking the deficit based on the number of electrons and protons inside of them.
Gravitational mass, the property of an object that creates and experiences a gravitational field, while the m on the right is inertial mass, a measure of resistance to acceleration.
Well, there's no resistance to acceleration, so there's just the fact that it takes energy to move things. You can't move it for free, but there's no resistance. It's not saying I will not be moved. No, it's just saying, of course you have to pay to move it. Of course something has to do some work. Something has to work. There's no free lunch. Things don't move for free.
Why should these two conceptually different properties be numerically identical? Scientists have spent a lot of time and effort experimentally testing.
Well, then they're garbage. They're not scientists, okay? Because this whole thing has no scientific credibility. It's weakly evidenced and it's silly. As an explanation, it's not even physical. It's not even physics.
Down to around 1 part in 10 trillion, that these two types of mass really are the same. But
there's no two types of mass. There's an electron, and an electron has it takes a certain amount of energy to move it from point A to point B, a certain distance. And it always takes the same energy to move it a distance as long as you're not applying any other force. So independent of any other force applied, there's always takes the same amount of energy to move an electron an inch. It's always the same amount. Always, 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 always. That's it. There's only one mass.
In general relativity, there is no mystery. All objects appear to fall the same way because Well, they're not accelerating. They're just following straight line paths through space-time until they encounter something that stops them. Like the objects in the rocket ship, they appear to accelerate at the same rate because they're not really accelerating. It's the floor accelerating into them.
Duh. But we're not talking about when you're not accelerating. We're talking about when the floor catches up and starts pushing you. And the fact is, you're going to keep feeling it pushing you. It's going to keep pushing you unevenly. It's going to keep pushing you from your feet up. It's not going to push your hands and your brain and all these other parts. So they're all going to stay behind, and your skull is going to move into your brain, and all kinds of other things are going to happen that'll be unpleasant.
Now, a lot of this might seem pretty far-fetched, as it did back in 1915 when Einstein proposed it. So he very cleverly came up with a measurable prediction that science...
Oh, it's just so bad. He very cleverly did any of this bullshit. He didn't do any of that, okay? It just was this bizarre happenstance of Eddington coming to the rescue, frankly. And that's it. Okay, Einstein was clueless and lost.
...scientists could make to test his theory. Imagine that this rocket ship is coasting through deep space. If you shine a light beam across the rocket ship, well, it'll do exactly what you expect. Light travels in a straight line and hits a point on the...
Right, so, yeah, it doesn't look like a wave, does it? No, it looks pretty much like a little straight line, a little bunch of BBs shooting their way across pretty fast. Yeah, little bullets. Yeah, it always moves straight. Always, 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 always. And Einstein believed that. And so what does Einstein say when you move the wall? Well, yes, the light doesn't give a shit that you move the wall.
The opposite wall at exactly the same height as the source. But now, what if this rocket is accelerating? Well, to an external observer, they're still going to see the same thing.
It doesn't have to be accelerating. The truth is, it doesn't have to be accelerating. It just has to have velocity. All I have to do is give the spaceship velocity, and the beam is lost. It's done for. It's not going to be able to hit the same spot on the other side, because the other side of the ship is moving perpendicular to the straight line the light's traveling. So he didn't even say this right. It has nothing to do with acceleration. It only has to do with the velocity caused maybe by acceleration, of course. I mean, everything has to accelerate to have velocity, so you can use acceleration, but the point is it's just velocity. This is basically just a speedometer. The light, if we could move at preposterously fast speeds, this light clock analogy would be perfect, because it would be basically a speedometer. The more the more the photons end up hitting the wrong place on the side of the ship, it would tell you exactly how fast you're going.
Light traveling in a straight line. But inside the rocket, during the time it takes for the light to travel across the cabin, the rocket will have sped up. So by the time it hits the other wall, it'll hit a little lower.
Right, it will hit a little lower, but it will not bend. Okay, so this is another wrong. You won't visually see it. Even if I fill the room full of dust, you won't see it as a bending laser beam. You won't see it that way. It'll hit the bottom. So it's going to go straight across as a straight line, and it's going to hit low, but it won't bend. Okay, so again, this is just nonsense. It won't do any of this bending crap. It's completely uninterested in this, creating an illusion for you. It's going to move in a dead straight path, and the wall is going to move out of the way, and that's what you're going to see. You're going to see the wall move out of the way. You will not see the light bend. You'll see the wall move away.
Than before. So in an accelerating frame of reference, light deflects down.
So again, it didn't deflect down. It didn't do any of that stuff. So it's completely wrong to say the light did something. The light didn't bend. The light didn't deflect. The wall of the spaceship moved away from the light. Nothing about the light has a bent line or a crooked line. If you're anything you want to draw it, it's here in space, okay? And then it's you'll see a dotted line, because you're going to move away. So you'll see the line move because you're moving away. So I'm moving away from the photon because I'm accelerating with the wall. So as I move, so the photon's going this way, I'm moving away from it. So I'm going to see it here. And then I'm going to see it down here. And then I'm going to see it down here. But it's going to do all of those things in a straight line. It's never going to have a curved anything. There's not going to be any curved appearances. it might be a dotted line going down, but it's not going to be a curved line.
Here, I am dramatically exaggerating the effect. Even if I were accelerating up at 10 Gs, which would probably kill me, the deflection would be on the order of the width of a...
Well, you know it would kill you, right? I mean, you know 10 Gs will kill you. But regardless, it wouldn't be probably. But that's a tiny speed. So why are you talking about it's a tiny speed? That's like 2,000 miles an hour or something. It's not very fast. 10 Gs. I mean, 10 times the speed of gravity. The speed of gravity is like 22 miles an hour or something. It's pretty. I mean, 10 meters per second it's not a very fast speed.
Proton. Still, it shows that an accelerating frame of reference will bend light. So Einstein
So it doesn't show that. It doesn't show any such thing. The light never bent, never even came close to being bent. The only thing that happened is the side of the ship moved away from the light, period. It moved away from the beam of light. It moved away. That's all that happened. You know, it's just wrong. And so the whole thing of Einstein saying, okay, now I'm going to make this special case where photons are twice as affected by gravity. So again, he's not going to say those words. But Einstein's prediction means that the only thing in the universe that's twice as affected by gravity, that is, it's affected twice as electrons, nope, just 1x. Protons, 1x. Steel ball, 1x. Human being, 1x. Only the special photon is twice as bent by gravity. That is, the photon experiences 20 meters per second gravity. So somehow a photon, when it's in the same exact location as I am, it experiences 20 meters per second gravity, and I only experience 10. You think there's any reason to believe that crap? And the reason why he even suggested it was because of this moronic equivalency crapola.
Light must also bend when it passes a large mass. But where do you find a mass large enough? Well, the only
Well, let's realize the sun isn't a very good large mass. So here we go again, right? The gravity on the sun is only 80 meters per second. It's only 8 times what it is on Earth. It's not that much stronger. It's not, huge, gigantic, monstrous gravity. 80 meters per second. That's it. Not that impressive. And then we know we can't do any of these experiments in the corona, and the corona is almost a whole radius away, so we already know that, well, now we're down to 4 meters per second.
This huge mass near the Earth is the sun. So the ideal experiment would be to look at light passing just next to the sun.
So why say that, all right? I mean, it's just so technically shitty. So he sits there and shows you Einstein's equation, does all this other stuff that's a little high end, and then he can't even explain this right. You don't do any experiment on the surface of the sun, but you can't. Because the surface of the sun is gigantic flames and shit. You can't do any visual experiments shooting light through gigantic flames.
And see if it is deflected. Say, light from distant stars. The problem was, of course, the sun...
Why not other planets? The other planets go, around the other side. Sometimes we're on one side of the sun. The other planet, like Venus, is on the other side of the sun. Why not watch one of them go behind the sun? I thought of that today, and I said, well, why didn't he even talk about that? I mean, that has to happen now and then. We're not, all the planets aren't on the same side of the sun all the time. Half of them have to be on one side, and half of them have to be on the other side, sort of rationally. So, I mean, we'd see them passing behind the sun. So why don't we do one of those experiments? Because those objects are pretty bright, relatively speaking. And we should be able to see them quite well without even doing time-lapse photography. We should be able to do a videotape of Venus going behind the sun.
It's just so bright you can't see stars right next to it. Unless there is a total solar eclipse.
So, right, or unless you're in the 20th century and you have satellites with cameras on them in space. And we've had them up there for decades now. Decades we've had cameras in space. And what's he saying? Unless we go back to 1918 or 1819 or whatever, 1918. Why? Why do we have to go back there? Why do we have to do that? We have all this modern technology. Why can't you do the experiment right? You do it from space. There's, I don't know, if Veritasium, maybe he doesn't know this. But you do the experiment from space, and there's 400 times better seeing. So you'll be able to see what you're looking for 400 times better if you do the experiment from space. So you can take the same technology, and it's 400 times better. So just imagine if you could buy like a magnifying glass, and I could make it 400 times more powerful just by moving it up to space. It's the truth. It's 400 times better. It sees 400 times more stuff, deeper, more resolution. 400 times better from space. Come on. And they've never done the experiment from space.
Which is exactly what happened in 1919. So Arthur Eddington set out...
So he's talking about an experiment. He's got to know the history is dirty as hell. There's all kind of controversy about the fact that they just quote mined the evidence. They took the plates that matched and kept them. They broke the ones that didn't fit. Really classic bad science all over the place. It's already a really hard experiment to do. You're looking for a tiny, tiny variation. Very subjective in the terms of lots of human error possible. Blah, 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 blah. Crappy experiment. Worst, Eddington said in his own journal. He says it. I wouldn't stake my life on these results because he knows how bad the weather was. He had shitty, he got 10% of the photographs he was looking at. So I just told you get 400% better from space. He got 10% of what he was hoping to get. So he had 10% quality to his photographs. And it's 400 times worse than it would be if we did it from space now. And you people are telling me we should believe that this is the experiment that proves something. It proves nothing.
To take pictures of the stars right next to the sun.
So they're not right next to the sun. Again, they're almost a full radius away from the sun.
During totality.
Oh, shit.
And what he found by analyzing...
Where there's only 40 meters per second gravity. It's only 4 times as strong as the Earth's surface. So clearly, if they really want to do this experiment, they should just do it off Jupiter. Jupiter doesn't have a gigantic... Once you get past the chemical atmosphere, it goes pretty clearly. It's a pretty hard line between the gas and empty space. And there's no corona and no heat problem, so there's lots of good viewing space there. And you're still fairly close to the center of the planet in the sense that you still have pretty strong gravity. So you probably have 40 meters per second around Jupiter.
In those pictures was that their positions appeared deflected by the precise...
So of course that's a huge preposterous and insane exaggeration, and the star wasn't behind the sun, so he did it with this star behind the sun thing, which is just a lie. The sun wasn't behind the sun. It didn't look like it was behind the sun. That's just a lie. So he did exactly opposite of what the real experiment was.
Amount predicted by Einstein's general theory of relativity.
So it bent twice as much. So instead of being by the Newton number, which is about velocity, right? Newton's numbers are all about velocity. So if you give the speed of light to photons, it doesn't matter what their mass is, it just matters what their velocity is. And that'll tell you how much they can be bent by gravity. Gravity is just a velocity equation. When it comes down to it, in terms of how much deflection there was going to be. It doesn't matter what your mass is, it just matters what your velocity is.
The result was twice the deflection some had calculated using a strictly Newtonian model.
So it was no strictly Newtonian model, it was using the g as the gravitational constant. So frankly, what Einstein's doing is basically saying there's a special gravitational constant for photons that's twice as big as the gravitational constant for regular matter. And that's all they did here, okay? You do the calculations, like I said, it's pretty straightforward. You're just multiplying velocity using the constant to decide how much the bending is going to be. And Einstein's saying it's magically different for photons. Photons are magically different. So the fastest thing in the universe is somehow twice as affected by gravity. There's no logic to it. There's no mechanism. There's no sense. There's no way to fit it into any kind of model and say that makes sense. There's no reason for us to believe it. It's just complete bullshit. And it's never been proven with anything called good evidence.
General relativity has passed virtually every test.
So this is passing the test. We did an experiment in 1919 that was overtly flawed, and lots of people were critical of it as being kind of sloppy science. And you're going to hold that up in 2020 and say, we proved it. And that's all you've got. And now you're just going to spew some propaganda about, well, we did lots of other experiments, but I'm not going to cite any of those. Yeah, coward. Why don't you cite them so they can be pointed out how, well, that's a scatter experiment. That doesn't have anything to do with gravity.
Put to it over the past 100 years or so. But there are still more things.
You just said, passed all these tests over the 100 years or so. You haven't passed the Eddington test. You haven't passed the show me test. There isn't a single show me test that you passed. And showing me that atomic clocks are screwed up, that you can break clocks with velocity, frankly isn't showing me anything. Because I can screw up how fast atomic isotopes decay. I can screw it up by just introducing more isotopes. I could just make them closer together and I can make them decay faster. So this isn't a huge surprise that I can screw up an atomic clock. Yeah, I can put it in a radioactive bucket, a bucket full of radioactive material, and the clock won't work anymore. Is that proving something? I don't think it proves anything. It proves that you can break clocks is what it proves. It doesn't prove there's any fucking time dimension.
To try. A well-known
so I haven't seen this. So this is obviously a commercial, right?
and empirically validated finding is that accelerating charges radiate electromagnetic.
So again, he just says it's proven, it's validated, it means something, that somehow we actually prove that a charge moving is creating something. It's shooting out crap, and it doesn't shoot out that crap when it's not moving. It's never been proven, that there's no evidence of it. They never see electricity going through a wire and know exactly what's causing the effect. I would clearly argue that the effect is clearly being charged by the fact that you're changing the shape of the atoms and now they're magnetic. It has nothing to do with electrons moving. It has to do with atoms changing their shape. It has to do with creating dipoles.
Radiation. So one conceptually simple experimental test would be to compare the behavior of a stationary charge in a gravitational field.
Right, exactly. So let's see them do that. A stationary charge in a gravitational field. And what would that charge be? An ion? Yeah, come on.
To a free-falling one. If a more Newtonian picture of gravity is correct, well then the stationary charge should not radiate electromagnetic radiation, but a...
No, isn't that funny? So that's exactly the opposite, right? I'm the one arguing that no, the Newtonian view is the charge is always charged. It never stops being a charge, and you can move it, and that makes it more effective in terms of changing. You're changing its position. Obviously, when you change something's position, like a bullet, you mean the bullet capable of boring a hole in somebody's head. But the bullet never changed from being a bullet. It was always a bullet.
Free-falling one is accelerating, and therefore it should radiate. In contrast, general relativity sees the free-falling charge as non-accelerating. It's just going on a straight line path through curved space-time.
Yeah, so isn't this convoluted? I didn't watch this part of the video, so I didn't know this joke was coming. But isn't that so convoluted? So they make up this fake straw man, which is, this is Maxwell's horse shit about this moving charges shit. This isn't Newton, okay? So the idea that a moving charge is somehow Newtonian, it creates a magnetic field or does some other horse shit, that was already their quantum-y crap, okay? That's their stupid magnetic moment bullshit. All right, that doesn't have anything to do with looking at it as a bumping particles point of view. So he's taken the straw man of his false lie that somehow it's Newton that says moving charges create something new, okay? And no, the simple physics says, no, the charge is always the same. If you move it, it has a consequence, of course. Anything moving is now dangerous, but it doesn't change anything. You're just moving the field, obviously. Obviously, it has a gravity. If I have gravity and I move the gravitational body, obviously now I'm moving the gravity into new places in space. I'm changing the environment for new places. I mean, obviously.
Whereas the stationary charge is accelerating, and therefore it should give off electromagnetic radiation. Now, thus far, logistical challenges have prevented anyone from actually carrying out this experiment, but what you believe will happen reveals what you truly think about the nature of gravity.
Now, I think they're always charged, and that's all they ever are, is charged. And then when you change their position, you change whether the atom is a magnet or not, frankly. And that's all you're changing. You're changing a neutral atom into one that isn't neutral from different points of view, frankly. But there is no, the electron is incidental. The electron is makes it happen in terms of changing the shape of the electrons, the atoms, but it's basically just the same way as they ionize atoms. The ionization of the atom is what's important. You don't need the electron to make a field. Its normal field in the new configuration of the ion is all you need.
Do you think that a freely falling charge will radiate electromagnetic radiation or not? Is gravity...
Okay, so, alright, so that's another point right there, is that, again, none of these people have really thought about what a photon is. So he just says, emit electromagnetic radiation. You can't emit electromagnetic radiation in a form that can be received with one electron. It's not possible. Because the polarization of all electromagnetic radiation is gigantic. And there's no way one electron can produce that. So obviously it has to be a composite object made up of the radiation being created by numerous electrons.
An illusion?
So that said
This episode
nothing.
was sponsored by Caseta, and so I used the sponsorship money to have a rocket ship built.
So he obviously is making so much money doing this horse shit that he can just piss it away. Ugh, sad.
Caseta by Lutron makes the smart light switches in the rocket ship. They also make remotes, motion sensors, smart plugs, basically...
Yes, do they make those toggle switches too? Oh, God. Pathetic. This is... yeah, it's just too pathetic. Alright, didn't have to do any drawing, I guess, so... but I was prepared. Just let you know, I was ready. Yeah, see, right there, I had the other camera ready, so I was ready. But anyway, enough of this. Until the next time and such, and so forth and whatnot. But this is garbage as science. Science shouldn't be done this way. All this hype, all this, I'm going to sell you. I'm not going to do a fair trial thing. Let's just admit the evidence is obscure. And we're all stuck trying to put a bunch of little weak, foggy pieces together to try to make this whole image. And we already know that quantum mechanics and Einstein's relativity don't fit together well at all. That one of them's going to have to go, and maybe both of them should go. These are all things they can see right on the horizon, and here they are doubled down, trying to sell you on the idea you have to believe in this bent space crapola. When, if you invest in it, I'll guarantee you'll lose your money in the future, because it's not the future. And it's sad that you're so resistant to understanding why it just never was a good idea. It was never well evidenced. It was just hyped. It's all this physics for 100 years of this quantum mechanic wooey crap is just hype, hype, hype. Really bad evidence. Alright, so till the next time and such.